Math without insight can fail. Today's literature overflows with descriptions of software problems, but many of the explanations offered miss the point. Often it isn't just defective code. Lack of insight in underlying concepts can doom a program before any code is written. The title of this video says it, Math Without Insight. It can make you believe you're rock solid until you crumble. The example chosen for illustration here is a complicated satellite, but you don't have to know anything about satellites or those complications. Without any math at all, I can explain to you why insight is essential. In 1968, NASA successfully placed the first radio astronomy explorer satellite, RAE-1, into an orbit at altitude almost as high as the Earth radius. Its small hub, containing all the instruments and controls, was surrounded by 4 long appendages. A simplified sketch shows the cruciform shape that was successfully used to maintain orientation near what was intended. There it is. Now I'll briefly depict this X-shaped satellite with exaggerated size, exhibiting the orientation it was designed to hold during its orbit around the Earth. After that cycle you just saw, orbital motion would continue in the direction of the arrow shown. At the position you saw last, tilting the X along that arrow is an unwanted pitch rotation. Motions like that happen with stabilization that isn't perfect. There are little wiggles called librations. They appear also for roll and yaw, which you'll see very soon next. Small rotations in those directions don't change the X image much. Visualization is improved if intensity is increased as appendages come forward and fades as they recede. First, roll. And then yaw. Now I can explain, but without math as I pledged, why this was so complicated. Each of those 4 appendages could bend in and out of the orbital plane. Bending came from multiple influences, all of them varying with direction, which of course was different at each point along the curved shape. From the next image you'll see why the flexure was coupled to the librations. That kind of bending looks like the pitch libration you saw earlier, but with the straight lines replaced by curves. So it's no surprise that flexing and librations occurred together. With many frequencies involved being close, neither action could be analyzed without the other. Next, you'll see all 4 of the deformation modes that were coupled to rotation. Here they are. The ones resembling roll and yaw came across more clearly in a side view. Now let me draw attention to the one that was labeled in plane. There's a lot to this, but for a quick explanation why it interacts with rotation, think of the moment of inertia. Because librations and flexing were both undesirable, a damper was connected, mounted at an angle skewed out of the plane of the X to dissipate energy as it would pivot like this. The skewed angle coupled the pivoting action to all four deformations you saw. That design was intended to counteract all unwanted motion. By analysis of each appendage's action, sure enough, each one's in-plane and out-of-plane flexure was coupled to pivoting of the damper. Two companies had contracts from NASA to write programs characterizing the motion to account for all the necessary interactions. The one written by a corporation in New England will be described first. They correctly modeled the coupled flexural rotational dynamics combined with detailed orbit dynamics. But including the orbit dynamics was unnecessary. It is a well-known principle that motion with respect to a satellite's mass center has negligible effect on motion of that satellite mass center. NASA already provided orbit tracking. Duplicating the orbit model added complexity, clouding that fundamental property of the flexural motion, leading to a design flaw that could have scuttled the first RAE mission. Due to the unnecessary complication, a fundamental issue went unnoticed. The damping was not pervasive. The damper could pivot, but not shift back and forth, left and right, up and down. So, for example, it was unable to counteract the kind of flexing that moves the hub away from the satellite's center of mass. A model for RAE dynamics was developed by myself and another co-worker from Westinghouse at the time. We analyzed all rotation and bending motions with coupling between them without duplicating NASA's orbit tracking. 4 appendages, each with in-plane and out-of-plane flexure, produces 8 modes. Instead of 2 bending states for each separate appendage, we formulated the states as satellite modes. You've already seen the 4 causing the damper to pivot and dissipate energy. Here's the undamped quartet. The center of mass, at the little o, still has the same history of position defined by orbital dynamics. Nothing changed there. But the analytical model showed the last 4 modes completely uncoupled from all other motions. When I made that presentation at Goddard Space Flight Center in 1968, one of the listeners from NASA uttered the word despair. With launch time imminent, there was no way to make a fundamental design fix. Fortunately, the appendages were made from material that provided enough structural damping to dissipate energy as they flexed. RAE-1 did not lose its stabilization. The rest is self-explanatory. Yes, the math has to be right, and so does the programming. But more than that is needed. You need insight. As promised, I spared you the mathematical complications and a ton of details. The bibliography, included for those interested, covers only the dynamics. There is much additional literature describing RAE's radio astronomy aspects.